Welcome back. We're going to now use electric to simulate with ltspice our inverter chain and get that all set up. We'll run into a few hitches, get it cleared up, and go from there. So we also get to watch the test message scrolling by today. Thank you very much. All right, open recent library. Open up the JElib, the library that we were using before. Since this is a simulation, we already put this spice simulator, this pulse voltage source in here, and I would really like to edit these parameters, but I can't edit them. Do you see that? I can't click on it. There's ways to do that, but since we're going to be using this a lot, how about we go down hierarchy and actually edit the symbol itself. This shows up actually in this library spice parts. It magically showed up. Read the manual and it'll tell you how that works. We're actually editing pulse IC, the icon, spice template, V, node name, plus, minus. It's just kind of a nice way to fill things in if that's how you like it. I'm going to move all this text out here is what our main task is. So we can edit them easier. Otherwise they get stuck and we select the part instead of the text that we want to do. That's all we need to do for this. Control S. We want to save that. We saved it, and we're going to go back to our inverter and this time delete it. Components, spice, pulse, put it back here, and we see that now our new version gets pulled in. Zoom in, and we see that all these texts are tagged with or associated with the pulse source, except now we can double click and edit them, which is exactly what we want. So zoom back out, select, wire it up, select, wire it up, and this pulse voltage, that's the one we really need to change. It goes from initial 0 to 3, but our power supply is 5. Change that to a 5. Rise time, fall time, 200 pico. Let's make the rise and the fall times to be 20 picoseconds, 10 picoseconds. 10 pico. This is spice. Pico, and then pulse width. Let's see, pulse and period. Do you want to? We'll keep it like that for now. All right, so 0 to 5. It starts rising right away. Starts going from 0 to 5 right away. Takes 10 picoseconds to rise, 10 picoseconds to fall. The pulse width on the top, the flat portion, is 3 nanoseconds. So this duty cycle is actually less than 50%. The whole period, the repetition is 6 nanoseconds. The top is 3 nanoseconds. But the bottom, the actual flat part of the bottom, is 3 nanoseconds minus 10 pico minus 10 pico. So it's not exactly 50% duty cycle. You have to do a little math in your head to figure it out otherwise. And I see something weird with this node, and we want to hook to minus. There we go. We had a blue line going across, and it looked like we were shorting it out. Okay, so we go back here. This is really nice. When we simulate this, what we want to do is know what nodes we're dealing with. If you double click on the node, electric tells you what the net name is. Net at 4. The middle one here, net at 5. Net at 6. That's the order that I drew them in, so there we go. That's what will show up in ltspice. We don't want that. Let's double click, change the name. Let's call it A0. Move this, click off, move the text up just a little bit, double click, A1, move the text off just a little bit so you can read it. This next one, double click or control I, A2, click off, drag it up. Now we have A0, A1, A2, click, add a wire, double click, and that is A3. There we go. Now we named all the nodes, so we know which one is which and don't have to deal with arbitrary names. Before we do this, let's just see if we can simulate it. Simulation spice, write spice tag. Oh my goodness. Cannot find the definition of model N, width and length of those two. Select OK, cancel. Let's look at this. This is the subcircuit for our cell, INV1. That's our cell. It has two nodes to the outside world, in and out. Some comments here. VDD and GND are nodes that are ground and, well, the power supply. Right now we don't have a power supply in our circuit, so that's not good. .global, that's a command that just says GND and VDD. Those nodes are everywhere. We don't have to, if we name them anywhere, they're connected. Global variables usually are a bad idea. Sometimes, especially for a digital part that we're doing, those two nodes actually do go everywhere. If this is an analog design, I would take off points for having global nodes because it's an invitation for trouble. Digital stuff for this is okay. So here's our pulse. This is the line for that. DC, it goes from node A0 to ground. And at pulse 0 to 5, we can look up the syntax for that. 3 inverters, 3 X's, X, INV, 0, 1, and 2. That's just the names of them. 3 instances of INV1, and you can see that they are connected in cascade, or series, but series really is not the appropriate term for that. If you remember, ltspice complained about not finding model named N. Here's our NMOS transistor. M, NMOS 0, that's the name of it. Out, in, GND, GND. 4 terminals. Here's the model name right there. It was just called N. Well, ltspice doesn't know what an N is. It knows about MOSFETs, but we named a model. We don't have a model definition. What we need to do is we want to simulate using the models of the transistors that we have. Let's tell ltspice how to do this. First, we need to get the models. Let's get the models. Those are at moses.com. We're going to find the latest test data on semiconductor, half micron, C5, that is our process. V37G is the latest numbers. V39 is not complete. We've been looking at this several times. However, what we want is we want to scroll down, BSIM 3, version 3.1 parameters, and so on and so forth. Copy this right here from the stars on. Now everything we copy here, these are the 2 SPICE models for our transistors. They are complicated. Control C, open up Notepad, Control V, plug them in. There we go. Now this dot model, it is a NMOS transistor, but this one they named it CMOS-N. We have 2 choices here. We can name this model anything we want. However, in electric wants to call an NMOS model an N, just N, and that's the easiest for us, so we'll change the model name here. We'll call that N. Scroll down for the P version. P version. There we go. One more thing we need to change with this is we change the model name. That's great. The other one is level. Level is the key number. It tells the SPICE simulator, it says that this model is a BSIM3. And they just use integers to describe it. Level 3 is the square law version. We're not using level 3. Level 49, that's for H-SPICE, the expensive SPICE. It's very good. But we need to look up what ltspice is, just to confirm, in case, so we're not invoking a model that we don't know what's going on. Hopefully it would be noisy about that and give an error, but we never know. So level 49, we want bsim3. Well, open up our ltspice help. Control F, it's only 239 pages. Control F is our friend, bsim3, enter. Alright, and so on and so forth. That's not what we want. Here we go. Scroll up to get to our line. M, MOSFET. This talks about the devices that are in ltspice. Can we show? I don't know how to show this where we are in the bookmarks. Okay, whatever. Okay, the MOSFET keyword, there's 4 terminals. There are 4 terminal devices. That's great. ltspice contains 7 different types of monolithic MOSFETs. That's what we're using. Here are the 7 models. The parameter level describes the model to be used. The default is level 1. All right, 1, 2, 3, 4. 4 is bsim. 5 is bsim2. 6 is MOS6. 8 is bsim3 v3.3. We're using 3.1, that's fine. Actually, 3.3 is newer, just has some bug fixes. Do you see that 49 does not show up in this list? It does not show up in the list because it's not, I don't know if it's going to give an error or not. We want level 8. So we'll go back to our text editor, replace level 49 with 8 for the NMOS, level 49 with 8 for the PMOS. Save this somewhere. Please remember where we save this. Save. What we're going to do is we're going to put this everywhere, put this text file in the same place where ltspice writes its files, which by default is wherever you save the library. Right now I have the library under this test directory. There it is, white inverters jelib. I'm going to save it as c5.txt. You can name it whatever you want, it doesn't matter. C5 text works for me. We've done it before. Yes. Let's go back to electric. So how do we get that? Well, let's do miscellaneous spice declaration. We're pretty much adding some text to our schematic, but it's a spice text, and we say dot include c5.txt. Click off. Now, if we say tools, simulation spice, write spice deck, it did not complain about the N. Well, we also didn't include an analysis, so it says, well, I can't do anything if you didn't ask me to do anything. There we go. Include C5 text. This is the lines that we caused to show up in the netlist. Let's also add an analysis. Miscellaneous spice code. They're nearly the same, but not quite. I'm going to Control I this one. And we're having some issues. Cancel. Control I. Hey, much better. Multi-line text, just so we can add multiple lines instead of slapping down these nodes. We can just dump all our spice stuff in one. We're going to do a .transient simulation. We're going to go for, let's see, 10 nanoseconds. Wait. 20 nanoseconds. And we're going to step by 10 picoseconds and go for 20 nanoseconds. You can divide that and find how many time steps there is. If you do like 1 femtosecond and go for 20 nanoseconds, this transient simulation will take a long time. Keep that in mind. Alright, so we say OK, transient, there it is. They don't line up, they're like centered here. Let's see if we can simulate it yet. Simulation spice, write spice deck. Hey look, this is blank. Here is our netlist. Here's our spice code that says a little note where it came from. .tran 10 pico 20 nano dot end. Okay, that's all great. Well, let's go pick visible traces, and let's see, VA0, 0 to 5, and so on. There's our square wave. That's beautiful. Let's look at A1. That's not beautiful. It's 0, does some weird things, does some weird things. This is not an inverter. Do you know what we forgot? We did not add the power supply. Think about that. If you don't turn it on, it's not going to work. So let's edit this again and add, actually we'll edit our include statement. Control I that, multi-line text, and we're just going to add it directly in Spice instead of dealing with the schematic stuff because that's a pain. VDD goes from node VDD to 0 for 5 volts. We also have VSS. It goes from node GND to 0, and it is 0 volts. We have to make sure that we can get GND and 0 hooked together. I think ltspice automatically does it, but let's explicitly do it so we don't have to remember. Okay, move this over here. Here's our setup. Here's our analysis, and we'll try it again. It's tools, simulation, Spice, write Spice deck, and it looks about the same. Let's look at some waveforms. A0, A1, that's nice. Let's do A0 and A1 at the same time. Hey, it looks like an inverter to me. How about we say zoom into this one. Where's our zoomy? There it is. Zoom in. Input, output. It looks kind of like an exponential decay. Do you see the dots here? I'm going to say mark data points because the points are what was actually simulated. The lines in between are just convenient. They're graphical only. Please remember that. One thing to note is you see how the points are not uniform. We have no point, no point, no point, no point, 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 not as many, not as many. Spice kind of adaptively puts these points in. So that's really nice. We let Spice do a transient simulation as it sees fit. If we need more of a curve here, we would have to explicitly set the maximum time step, which was 10 picoseconds, to less than that, and then we can move on. One interesting question is, why does the output go above 0, above 5 volts? I thought the power supply was 5. This is digital. There's no inductors. Well, there are capacitors. I'll leave it to you to figure out why it does that. It does. It's very important. It always happens, actually. However, let's see. Let's zoom back. Zoom back. Wait. Zoom out. All right. So we have this, that. That's nice. Let's add another A0, A1, A2. We're holding down Control to see all these. Zoom in here. Now this is why we have the inverter. So blue to green, that is the first inverter. And then green to red, that's the second inverter. There's an inversion in between, right? But this is why we want real inverters to drive our setup and just make it just works better. It's, I don't know how to describe it. It's a realistic simulation condition. It's more like going to the lab. If we just took between here and here is the delay time, it really would not be true because the input waveform is really a sham. It's Spice only. What we're looking for is the delay between, let's go back to electric. We really need the delay between A1 and A2. So that is green and red. We can add some cursors here and so on. We need to Add traces. Mark data points. Tools, view, plot, visible. Oh, what is it? What is it? What is it? I don't remember. Go back to ltspice's PDF manual. Right here, ltspice help. Look through the table of contents. Waveform viewer. Attached cursors. 2 cursors are available. You can attach a cursor to the trace by left-clicking the mouse on the trace label. Got it. So A1. We got it. We clicked on it. There's trace 1. Now we have to put this at 2.5 volts. Look at the right here that tells us where it is. Can we just say 2.5? No, we can't even write it in there. So we just get it as close as we can. 2.498. Left click over here. Attach cursor second. And then right click, attach cursor first. So 1 cursor. Attach cursor second. There we go. Now we have 2 cursors. So 2.5 volts. 2.5 volts. We have to be very careful. And now we want the difference in horizontal. This delay, 50% to 50%, that is the propagation delay from low to high on the output. So that is TPLH. And it is, in fact, 73.8 picoseconds. I would stop at 3 digits because we had to hand place these 2.5 volt markers, if you remember that, and they're both not even at the same. All right, there we go. That's measuring with ltspice. We simulated it. Can we march down, go left and right, zoom on here, zoom to the full, and then we measure the other one, zoom in, measure, and so on. So we have A1, A2, green to red. This delay is much shorter. That's how it's supposed to be, because that's how we designed it. And that is simulating with ltspice. You can stop now watching if you want, but we're going to do some really tricky thing, because this is a trick we're going to do to make our schematic entry much, much faster when we have lots of items to enter. Actually, that will be another video.